everyone. Welcome to this edition of the NITheCS Colloquium. My name is Francesco Pedruccione. I'm the director of NITheCS, but today I'm very happy to introduce to you a local uprising star. Yeah, Dr. Johané Nienkemper-Swanepoel. Sorry, my Afrikaans is ridiculous, but anyway, I'm trying my best. Johané studied at the University of the Free State, where she is also coming from. Yeah.
Yes, originally.
But joined Stellenbosch University in 2013 and is now a senior lecturer in the Department of Statistics and Actuarial Sciences. And this evening, she just been awarded a Research Excellence Award by the DVC Research and Innovation. And I think she collects the prize tomorrow, Thursday.
Yeah, it'll be official then.
Okay, so well done. Congratulations, really well deserved. And today she will tell us something about her research that probably led to the prize. Yeah. So we are very glad that that you offered us to share your wisdom with us and your practical wisdom. Yeah. So we are very looking forward to that. Thank you very much.
Thank you very much. Thank you for all for attending this seminar, and thank you for the invitation. I would also want to say thank you to my family that's joining online. So it's always nice with these hybrid events. So I want to just give them a little shout out as well. So today's presentation is joint work with Dr. Raisa Ghani. We worked on a package this year, started out in May, and then we published this package, and it has grown since then. I'm also going to show you towards the end an application, which is very exciting, for which we've used this package, and also it has helped to develop this package even further. So the aim is dynamic biplot visualization with the package we call moveEZ. And you can see all of our details on there. We're not going to read through that. So that's me and Raisa there. We got the opportunity to go to Melbourne in May. This is where we started work on the package. So this is at our door at Monash University, where we spent 2 weeks to work on the package. So also in Raisa's absence, this is very much our joint work, and it's a privilege to, on behalf of her or both of us, present this package seminar. Then a personal note, home life, just so that it's not just professional. So on the left, you see my husband, Franre, and our little miniature Dachshund, Marmite, and she's recently received her gold canine citizenship, so very well behaved, obedient, yes, for our little Marmite, so just something from home. So then more serious. Okay, so why are we here tonight or this afternoon? So our package moveEZ, some people say movies, which is perfectly fine. As you can see with our logo, it is animations, and it's so fitting that we're in a cinema tonight. We just need some snacks, popcorn to fit with this logo. So you can see that we're already in version 1.1.1 with some additions that we continuously add to the package. So just some background and also disclosure, the talk is not very technical. I want to show you what you can do with the package. But for that, you must have some background on, how can you use it. So in a typical setting, and also for version 1.1.1, we only focus on multivariate continuous data sets. So you would start with the data set X, consisting of n rows and p variables, or columns, sorry. So the n rows refers to our samples, observations, and then the columns referring to our continuously measured variables. But in our context, we have some kind of a factor. We think of time, but it can be a factor that is fixed. If you think of experimental design, there could be different phases of an experiment. So anything that is measured or captured at different phases or through time, that is something that's then additional to our data set X. So if you have this time aspect or this factor you want to incorporate, one way or a very primitive way of doing that would be to construct separate visualizations to investigate what happens at these different phases or at different times. But this can be very cumbersome if you have a lot of time levels or a lot of levels or phases. So this is where moveEZ started, is we wanted to incorporate a dynamic way of looking at a visualization that can change over time. And we first looked at it from a time aspect, but as I said in the second example, we'll look at an experimental design aspect. So firstly, it's to visualize sequential changes in the data. So a biplot, what is a biplot? It's a visualization where we simultaneously visualize samples and variables. So if you think of a scatter plot that you have learned about at school level, you would have a vertical axis or horizontal axes, and you would have all of these samples that are scattered along this plot. And then you would be able to read off the values from these axes. That is your scatter plot. Well, a biplot is a generalization of that. So bi meaning two modes, so the samples and the variables, and you can have many, many axes representing your variables, not just the two that you are familiar with from just a normal scatter plot. So these biplots are based on singular value decomposition. And just to illustrate this in a very simple way, it's a decomposition of a matrix into three matrices. On the left and the right, you have your singular vectors, and in the middle, you have your singular values, which is a diagonal matrix of a decreasing values that you would see on your diagonal. So what we aim to do with biplot visualization is start with a high dimensional problem, approximate that in lower dimension, typically in 2 dimensions, but we can also visualize in 3. I'm not going to show that tonight. So we would get a lower dimensional approximation in 2 dimensions. So to get the representation of the samples and the variables, this is typically what you would do. There are various ways of scaling and fancy things you can do. So this is just a basic way of constructing a biplot that I'm showing here. So representing the samples, which we typically call Z, comes from the data itself, and then the right singular vector, and then the variables are expressed as initially starting as vectors from our V matrix that you see there. So it's not very complicated to start with. So that is the biplot that I would be referring to tonight. So Z's, the samples, V, the variables. So our first application and how we've built the methodology, we started with this data set. So I always like to just say you can poke a lot of holes, I think, into this data set, but keep in mind, we wanted to find a real data set, build methodology that can tell a story, and then hopefully later we can engage with climate scientists and get their data and try and collaborate on that. So for the examples that you see here tonight, we're going to look at a period 1950 to 2020. And these are not decades, these are actually 10-year increments. So we're going to look at 1950, 60, 70, and so on. And these are all aggregated monthly measurements that we've extracted from era 5. So it's publicly available data. And we've chosen these African regions as demarcated on that map. So these regions are allocated by the IPCC that you can see there. And I've added a very small link there if you want to go and see how these regions are demarcated. So we wanted to start with variables that we can understand, right? Because we are not climate scientists. So we thought, okay, precipitation, that's easy to understand. Daily evaporation, mean temperatures, soil moisture, wind. And then we also included a standardized precipitation index of 6 months, which turned out to be quite a joker variable, you'll see. But the other ones were variables that we could understand from our just understanding of weather, generally speaking. So here, as we can see, we have a grouping variable, which are the regions. And then we have a time variable, which are these increments that I have, the 8 time increments. There are 10 regions in total. And then I have the 6 variables. And then these are monthly measurements. Okay, so we'll look at the dimension of the data set in a bit now. And with now, I mean now. So this is just to give you a snapshot of how the data looks. So I'm just going to hop through this so that you can see it is changing over years. And I said we're stopping at 2020, so that is our final year. And then the monthly measurements, so 12 measurements per year, per region. And then we have the 6 variables, as you can see there. Right, extracting the data into this format, I don't want to get sidetracked, but if anyone needs tips on how to get the data from era 5 into a workable R data frame, that is quite an exercise. So I'm happy to chat to you about that and share a notebook, because you have to work via Python, do a whole lot of wrangling to get it into a data set that you can see here, but it's worth it. Okay, so just another advertisement is biplotEZ. Professor Swanepoel also had a seminar similar to this one a few months back, and she spoke about biplotEZ. So that is the backbone of moveEZ. So all of the calculations of the biplots happen in biplotEZ, and we then pipe from biplotEZ's object onto our functions. So just to show you a static visualization, a PCA biplot, so a principal component analysis biplot of the Africa climate data that we just looked at, that is how you could visualize that. So just a little bit of a recap of what happens in this code chunk. So in the biplotEZ package, we have a biplot function which formats the data correctly, and then you pipe that to whatever biplot you want to construct. So this is a PCA biplot, and we want to color code according to those 10 regions. So that is specified. And then we have these aesthetic variables or arguments that we can change within the string of functions. So the samples have a specific color and opacity, and the axes also have their own colors. Okay, so I just want to spend some time on the interpretation of this biplot because we're going to now move deliberately through the moveEZ functions to then see what are the gains of working in a static versus a dynamic or the other way around. Okay, so to interpret a biplot, we look at the correlation between the variables as a starting point. That's what I like to do. So to look at the placement of these axes, where you see the label in biplotEZ and in most biplot packages, that label indicates where the increasing values are. So if you see that soil moisture, I want to use this pointer. Right, let me see if I can, there it is. They showed me how to use this very sophisticated pointer, and now there we go. Okay, I'll just use it once. Okay, so those two variables are highly correlated, positively correlated, because their labels are placed there on that same angle, and they are in the upwards direction there, so with the increasing values. So a high daily evaporation is associated with a high SPI 6. Then we also see the accumulated precipitation and the soil moisture highly positively correlated. So again, high values in both those variables would occur simultaneously. We see a negative correlation between wind and temperature. So an increase in wind is associated with a lower temperature, okay, which also makes sense intuitively to us at least. So that is one of the first things you can see. You can see temperature is not correlated with soil moisture and accumulated precipitation. So those are the initial interpretations that you can do. Then you can individually go to these points and project them to the axes orthogonally to try and read off the values to see what the approximated measurement is. But from our point of view, we won't look at those specific calibrations. We want to see patterns and trends. That's what so we want to get a feel of how these regions change through time. How does the relationship between the variables change over time? So holistically looking at, can we track changes? That's what we're trying to see. Okay, and what we see in this PCA biplot is all the time points combined. So at this stage, we can't see anything about changes over time. It's the entire data set that is fed to this biplotEZ object. Okay, so back to moveEZ then, we have two variable frames or frameworks that we work with. The first one I'll show we call the fixed variable frame. What that means is we construct a biplot from the full data set, so the one that we've looked at, and then we achieve animation by slicing through the Z, the samples that we've constructed from the singular value decomposition, but the V, the variable vectors, remain fixed. So you can think of the biplot I just showed you and then suppressing certain years to be able to see what the display looks at for a certain time point. So that is what we refer to these slices by just slicing 1950, slicing 2000, whatever the year may be. So to get that static frame or fixed variable frame, the first function in the moveEZ package we call moveplot, and it consists of these arguments, which I'll just quickly run through for those who are going to apply the package tonight after the seminar. So you have to start with PCA biplot from biplotEZ as I showed, and I just call that object BP. Okay, so BP is then piped to moveplot. And in moveplot, you would have a time variable, which is now going to be the years. And you can have a group variable, which in our case is the regions. And then holes, what this argument means is, do you want to see the sample points individually, or do you want us to construct convex holes using the periphery of those samples? So the external periphery of all the samples and constructing a polygon over those regions. So it depends. The samples, if they are plotted individually, can look very over plotted, difficult to see, not as legible. So the holes help to track the area size to see other changes that might be missing, or not missing, not be exposed when you only look at the samples. And then sometimes your variables have a low inertia, so they don't have a lot of explained variation, so it's difficult to see the vectors. So you can manually play around with the scale factor that's in the function as well. Then very importantly, we have the move argument, which then is going to distinguish between a static faceted plot or an animated biplot. So if move is true, it will move. If move is false, it will not move. So that's very intuitive. And then something that came in one of the more recent versions of the package is the shadow argument, which creates this sense of burn in so that you can track the movement over time with the opacity going, less and less and less. So it looks like the shadow that is following the points through time. I'll show you how that looks. So those are the arguments in moveplot. And as with biplotEZ, moveEZ does not want to complicate this for the user. So there's not a lot of arguments, which of course then means the user does not have a lot of control. But all of these functions are available on GitHub as well. If there's something specific you need or you want to add, I'm sure you would be able to do so, but you can also just log an issue on our GitHub repository and we can add it. That would be great, actually. Rather do that. Okay. So here's how it looks. So in the first example, maybe let's just quickly run through what happens in here. So in moveplot, the time variable, I'm just going to try and select it, year. We have our group variable region. Holes is false, move is false. So because holes is false, it's the samples that we see, and move is false, that creates a facet, as you can see. And each facet has a biplot, now separating the samples per year. You'll see, because it's a fixed variable frame, the vectors are the same. And what's different now from what I've shown you from biplotEZ, we don't use the calibrated axes here. There are various reasons for that, but because we are going to move the display, it becomes very difficult to track if you have all of these calibrations. So from an aesthetical point of view, and also if you just want to track movement and patterns, you're not necessarily going to go and read off a calibrated value. So the movement is what is important and the overall changes that you can observe. So I'm not going to stand still on this one because it is quite difficult to go and look for subtle changes. What this does show us quickly is we can see now where the regions are scattered over time. For instance, 1980 has less horizontal dispersion if you compare it to 1950. So you can quickly see stuff like that, but the true changes will be difficult to observe in this display. Right, so this is where it gets fun. Now we animate. And with the animations, it's, I want to say, easier to see at first if you look at the convex holes and not at the samples because they move a lot. And because you have 12 measurements per year, per region, there's a lot of moving parts in that display. So just on the function calls again, so holes is true, move is true, which then creates this animated biplot. And again, the fixed variable frame is now, there's less going on, so it's a little bit easier for us to track changes. Easy is now an overstated word. What I suggest is focusing on one color and just seeing how that area changes over time. And what I will do is I will say the years out loud to give you the opportunity to just focus on that color. So I'm going to look, I always like to look at Sahara, year, and ARP because they're together. But I mean, pick your own color, and here we go. 1950, 60, 70, 80, 90, 2000, 2010, 2020. So I hope what you could see in your convex hull is that there's a change in how the area relates to the vectors. And remember, the vectors indicate specific measurements that are taken over time. So if, for instance, like I said, I like to look at Sahara, the blue left convex hull, if you see how the variation changes over time in the horizontal direction, here it's larger, becomes smaller, larger again, smaller, but you can see that it lengthens over those vectors. And the vectors represent, if we focus on temperature and wind, that is a change in the observations for those variables over time. And that, of course, gives us insight into seeing how these variables change over time. I'm not here to give any solutions or specific reasons. I'm just trying to expose things that we can actually see in the animation. Okay, so let's see what the package can do with the burn-in. So as I said, visually, this is captivating for us to see the burn-in. I don't know how good it is for interpretation, but let's see if we start again at 1950. It's going to start fresh, moving to 60, moving to 70, 80, 90, 2000, 2010, 2020. Okay, so I'll show you in the last example how this can be used if you have unbalanced examples, because then you can see over time which observations are continuing and which has already stopped. So you can see kind of a dropout rate, for instance. But here you can also see that the convex hulls are definitely easier to interpret if there are a lot of things moving. Also, the hulls don't allow for the shadows. The shadows are only reserved for samples. Okay, so that's moveplot. Now we're going to show you how the variable frames can be dynamic as well. So in this framework, we then construct separate biplots per time point. So in the previous example, we had 1x, and it was a PCA, a biplot solution of the entire data matrix. And then we just sliced per time point that we were interested in, whereas now we're going to construct, for this specific example, 8 separate biplots. So they would all have their own axes, vector representation, and of course their samples. So let's see how that would then change. In the package, this is called moveplot2 for a dynamic variable frame. And then the other arguments carry over to moveplot2. What is additional in moveplot2 is that you now have control to reflect about the X and the Y axis or both. So I'll show you why you would maybe want to do that. And if you see that one of your time points are not aligned with the rest, you have also the control to then reflect that particular point. And you can do this, we call this admissible transformations, because it's still going to preserve the distances. And that's what is important in the biplot interpretation. So you can reflect, rotate, and I'll talk more about that in moveplot3. But for now, you as the user will have the power to do this. Okay, so moveplot2 then. The first thing that I want you to just see is we have different vectors now. So in moveplot, you had the fixed variable frame and then the suppressed samples per region. Here we now have individual biplots per time point. And what you can see is 1950 is resulting now in a reflection about the x-axis. So you can see that region I prefer to look at, ARP and Sahara, it's now on the right of the display. But the other ones are aligned in the way that we saw it previously. Let's look at some of the variable interpretations. So looking at the vectors, how have they changed over time? We can see wind and temperature remains negatively correlated. If you quickly run through here, you'll see that that variable relationship remains the same. I previously mentioned that SPI6 is our joker clown variable. And you can see how SPI6 is moving around, changing correlations with the variables in these different 10-year increments. And well, there are reasons for that. Firstly, if you see the SPI6 in some of the biplot displays have a very short vector. So it means the variation explained in that vector or variable is not as good compared to the others. In here, I won't show you fit measures, but that's definitely something to look at to see how much predictivity is contained for that vector, and then maybe decide to take it out of the visualization. So those are things that you can do in your analysis process. But for illustration of the package, we can see now, okay, we have 8 different biplots which can be interpreted. Then looking at the move plot of this, here I've aligned now to that 1950. So maybe let me just go back. Sorry, I want to go back to the facet. So 1950 was the only display that was reflected. So in the next code line, you'll see that I now align the time to that one. So that is the time point that needs to be aligned, and it has to be reflected about the x-axis. And what that does is that display is simply reflected now, and when it's animated, it won't jump around the x-axis, which would be very disturbing while interpreting this. So moveplot2 then allows you to be able to do that. So now we have the moving axes as well. With 6 variables, it's manageable to keep track of these. But now you have to kind of choose a variable and choose a convex hull and decide which aspects are you going to try and track through time. But that's definitely something that you can do. So if we, for instance, look at the West African region, this, let's call it purple magenta color. I like the area of this particular region. You can see how it really changes over time. So there's 1960, 70, 80, 90, 2000, 2010, 2020. So we can see there are changes happening in that region over time. It would be the work of the climate scientists to go and see what is happening, you know, what kind of variable interactions are changing, what could explain certain changes. But this really shines a spotlight on where the changes could be. Right, then our last function in moveEZ is moveplot3. And I've already kind of gave some of it away with my explanation of the admissible transformations. So this procedure is very close to my heart. Spent many hours, months, years looking into this. And it's called the Generalized Orthogonal Procrustes Analysis Algorithm, in short GPA. And what it allows you to do is apply configurative matching by setting a target configuration or visualization, and then sequentially or iteratively matching test T configurations to that target. And this is then updated in this iterative algorithm. So of course, you kind of know where this is going. We have 8 time points, biplots, and we want them to be aligned optimally. And what we've done in moveplot2 is a manual solution. So we saw 1950 is kind of out when we looked at the x-axis, and we could reflect that. But to automatically or automate this, you can use moveplot3, in which 4 admissible transformations are applied: translation, scaling, rotation, and reflection. And as I said, you set a target in this algorithm. Typically, the target is not a new configuration, it's average. So to encapsulate all the movement in the biplots, and then all the remaining or the test T configurations are then matched to that average centroid configuration. But you can, if you want, set a target. The only restriction is it has to be of the same size. So I'll show you what I mean by that. So this is from Borg and Groenen, Modern Multidimensional Scaling. And I really like this illustration of explaining what happens in orthogonal Procrustes analysis. So just assuming you have one target, one test T, and of course we generalize that to multiple configurations, but just to get a sense of how this works. So if A, this rectangle we see in panel 1, is the target configuration, and B is the test T configuration in panel 2, we want to match B to A. And we can see already it's of course smaller, so we need some scaling. And we can see that A1 is in the right upper quadrant and B1 is in the left upper quadrant. So there's a reflection that would be required for A, or rather B, to match A. What we see is that they are both centered, right? So no translation will be required. They're already at their origins. But what you see then from panel 2 to 3 is you can see that there's a reflection and then a rotation, and then when it's pulled, it's then scaled. All doing this by still preserving the distances. So that's why it's called admissible transformations. And this methodology is then applied to moveplot3. So I'm going to show you two cases. So default is target null, so that means the average is used of all the biplots. And then I also specify Africa climate target that's in the package, which is 1989. So I'm biased towards that year. That's my birth year, right? So there's a reason why it's included in the package. But you can see I said it should be the same dimension. So it has month, region, and it has the same 6 variables. It doesn't have to have the same number of rows as the entire X has showed you. Here it has to match each of the time slices X. So X1 to X8 that I showed you. And just because it is here, I can quickly just jump through it and we can see that, okay, it includes all of the regions and it includes all of the months. Right, so in the first example, the target is null, as you can see here in the code chunk. So it means it's taking the 8 biplots, getting the average configuration, so taking the average of all the coordinates, and then mapping them and updating them iteratively with those 4 admissible transformations. And what we see now is a move plot of still the variable frame that is not fixed. So we see the moving axes and we see the moving holes. But now they are optimally aligned. It's not a manual fix where we just reflect one of the years. This is now through GPA optimally aligned until a squared distance is minimized. So a lot happens in the background. If you want to use the variable frame that is dynamic, moveplot3 would be a better, I would suggest that would be a better option. Because of the optimization of the alignment. And then lastly, I just show if you then use a set target, so the 1989, the only big difference now is that it is reflected about the x-axis. So 1989's default biplot would have that layout, but it doesn't change anything in our interpretations because again, we look at patterns, we look at movements, we look at the magnitude of the vectors, and we are interested in how the areas change over time. And now what this means is because remember, we've mapped it to a specific year. So it's basically showing us differences per decade. So 1990 at the moment, according to its mapping to 1989. So basically, how much does 1950 change with 1989? So detecting differences then with a specific target, whereas the previous one allows you to detect differences on average. So it depends really on what you want to see, but it allows you to look at both those views. So to quantify the movement of moveplot3, there are these 5 measurements. So I'll quickly run through those. The procrustes statistic is based on this GPA. So it's a value between 0 and 1, and you want that to be small because that quantifies the movement that the testee has to make to match the target. So how much changes does, say, 1950 have to make to match the group average? So you want that to be small to show good fit or, you know, non-noticeable changes. And then we have the congruence coefficient, also a value between 0 and 1. You want that to be large, so close to 1, which then says that the patterns that you detect are similar. And then we have 3 bias measures that you can see there. And when you compare the bias values with each other, you want that to be small. So they can't be interpreted in isolation, really. So to get access to this, you would start again with your biplot object, plot this or pipe this to moveplot3. And I've used the Africa climate target here. So we're comparing it to 1989. And then you pipe that to evaluation, which is how you get access to these 5 values. So on the screen, I've just printed the summaries for us. So maybe let's look at large values of PS, just to not make this an hour-long discussion. So what you can see is focus on the PS value. I said we want it to be small. So this is 1950 and 60, 70 and 80. 1990 and 2000, and then 2010 and 2020. So the largest PEZ value was for 2000. That's what I prepared. Is it correct? Did you also track with me? So just looking at PEZ in isolation, it's the largest one, meaning that 2000 changed the most to match 1989. Okay, that's how you interpret that. You can do the same with the bias values, because with the bias measures, it's trying to see how much does the coordinate change in 2020 to match 1989's coordinates. So easier to look at is just the line graph. Okay, so what you can plot from the package is a line graph to quickly track where changes occur over time. So there is a little spike here at 2000, which is where we detected the PEZ value being slightly larger. These are marginal differences, right? But for the purpose of the example, we would say, okay, 2000 is working very hard to match 1989, which means there's a big, in air quotes, difference between what we observed in 2000 when we compared it to 1989. Okay, and then you can also look at the fit values. So the Procrustes statistic versus the congruence coefficient. And there's that spike that we observed in the numerical summary. So that summarizes our Era 5 application. I think we're still, yes, the rest, I'm just going to show you some graphs and an interesting application. So the first part of the talk was how to use moveEZ and the functions that are currently available in the package. And then we have this lovely collaboration with collaborators from Northwest University. So Professor Rolof Kutzer and Professor Hein Nieuw-Margus. They saw our moveEZ package and they said, well, they're using static biplots and maybe we can work together and try and expose things that would be missed in a static biplot. And it really is very interesting. So I'm just going to read the application as it is there. So it's a statistical analysis of emissions and performance of a wood-fueled stove. And there's also an integrated oven in this stove, and it's using local hardwoods. And it is a social impact project because this is the oven that they have developed to source to these South African homes. Sorry, I'm looking at this graph now. Maybe I should just start there. So this is the oven that they've developed. And you can see that there are two plates. So the stove option, and then there's also an oven option. In the hopper, this is where the fuel or the wood is then supplied. And then there's this chimney to the right. And we're looking at the stove from behind. And then on the left here, we have the combustion chamber. Okay, so that is the diagram of how this oven works. You can see here, this is exactly images from this oven where the wood source of the fuel is given. You can see this handle here is where the oven door is opened. So wood is a preferred energy source for cooking. And of course, it holds a major risk in a small space because of emissions of what we call household air pollution. So in this study specifically, the emissions and the cooking efficiency of the stove and the oven is measured. And the stove is called the Flamingo stove. And from what I understand, 50 has already been rolled out. There's also a subsequent study on this using coal stoves. But for this study, we're looking at the difference in the emissions using 4 locally used or sourced wood. So what is measured? The measurements were performed every 10 seconds and a total experimental time of about an hour and a half, 90 minutes. And then things that were measured directly, the mass of the stove and the fuel. So how fast would this wood burn? So grams per minute were captured to see which of the 4 wood species had a longer burning rate. Then dry gas fractions. So yeah, I must tell you, only have metric chemistry, right? Okay. But these are the 5 gases that were measured. So the nitrogen monoxide, sulfur dioxide, carbon monoxide, carbon dioxide, and oxygen. And then they have a diluted and undiluted way of measuring that. Various temperatures in the oven and that chimney that I showed you to the right measured. And then they have pot temperatures looking at cooking efficiency. I'm not going to look at the cooking efficiency tonight, but that's also part of the project. And then very important is the particulate matter concentration. which are these small particles that is very dangerous for you to inhale. So of course you want that to be as low as possible. So ultimately this is a factorial design where 4 different wood species are used. The oven component is sometimes switched on or not. So that's also a controlled factor. And then the power phase, low, medium, high. So high is the initial phase where you have most heat. And then once the wood starts to smolder, then that goes into the low phase. So those are the factors that we then try to isolate and look at. And since you've now spent 40 minutes with moveEZ, you can see, oh, I can use the oven as a fixed factor to move through time, or I can use the power phases to move through time. So we definitely want to see the difference between the wood species. So they are our grouping region, but the time region can be ovens or phase. Okay, so I'm going to show you all of this, but what the objectives were is we want to understand the process through targeted visualization. As I did at the beginning, of course, it's important to understand the correlations of the variables. Here we want to see how the different wood species react in this whole process. What is the effect of the oven? And of course, most importantly, what are these emission concentrations? How are they associated with the wood species? Right, so first a static visualization. So using moveEZ, that's also possible. So firstly, what we are looking at is, again, a PCA biplot. The color coding is the wood species. I didn't read it out loud, but sicklebush, mupani, leadwood, and black wattle is what we are looking at. And then importantly, to see the correlations between these gases that are measured. So we can see this dangerous particulate matter is positively correlated with nitrogen monoxide, a negative strong correlation between carbon monoxide and dioxide, which makes sense. And then a negative strong correlation between SO2 and this PM and NO. And what we can also see is that leadwood, the green samples, are associated with higher levels of CO2. And that one is really the only one that is separated from the other wood species. So this is, again, looking at it from a static point of view. But using moveEZ, we can then track changes in the wood species. So on the left, the oven is not on. And on the right, the oven is in use. So we can see when the oven is not in use, this is more dispersed sample behavior that we see. We can see that there's more SO2. And what I understand from the engineers, it's a cleaner burning of the wood when the oven is not used. So there's better combustion. They explained it to me that way. So point is, it makes complete sense to them. What is wonderful to hear when you do these visualizations is that it does make sense in practice. And what we can see is that, again, this leadwood associated to the higher SO2, and that it's even more so separated in the oven state of this stove than it is when the oven is not being used. Moving through the phases. So as I said, the high phase, H, is the initial phase, medium heat, and then the low heat phase. So that's towards the end, the smoldering phase. And we can see this concentration of the sample points in the high heat phase. And whereas the wood starts to burn out, we see that the emission starts to change. So that's also very interesting to see that there's, of course, a difference in the profile of the species in the different phases. So that was all of them showing you move plots. So that is a fixed variable frame. But of course, if we use a dynamic variable frame, there's a lot more that is exposed, because now we construct separate biplots for each of these phases. What's very interesting to see is the correlation of the emission factors change in the different phases of this heat source. So that's a very important finding. If we go from right to left, we can see this relationship of PM with CO2, highly correlated. But as we move to the medium phase, it is not correlated if you see a 90-degree angle between those vectors. And that remains uncorrelated through the entire phase of this experiment. Another one that is still important is this negative correlation between CO and CO2, which in the high phase is almost uncorrelated, but as we move through the medium and the low phase, we see that negative correlation between those two. And also another important one is the relationship with SO2, which we see in the low phase, we see SO2 is negatively correlated with PM and NO. So the point is, the dynamic frames expose a lot of this process that would have been lost in a static frame. And what I want to conclude with is just showing you an additional objective of this project is looking at the emission concentration levels. On the right, the diagram shows us where different temperatures are measured in the stove and the oven. And then each of those temperatures are represented in a vector. So sorry, it is a very overplotted, right? We need some additional work to be done in the next version. But what we can see is, for example, these three vectors at the bottom, they are placed in the oven here. I'm just going to show you this value, and this value. So just out of interest, so they are highly correlated, and that is where they were placed in this oven. And then again, we separate according to the wood species. And in here, you'll see the gases that I've highlighted throughout the others as well. So here we're going to look at two animations. In the first slide, it's going to be the phases that we are animating through. And what is important just for our quick discussion is to look at the behavior of the 4 wood species. And you can again try and focus on one of the axes, maybe more interesting to look at CO and oxygen because it's easier to see. And the aim of this one specifically is to look at the differences in the temperatures measured in these stoves using the different woods. And we can see that sickle bush, the purple one, is the most variable if we just look at the movement throughout the phases, right? And if you think about what the shadows tell us here is the movement through the time factor here, high, medium, low, and where the observations stop, that is the end of the burning rate process. What is actually nice to see is in the next one, where we now show increments of 10 seconds. As we said, the measurements are taken every 10 seconds for this 90-minute frame. And now we can see that Mopani and leadwood are the ones that take longer to burn out. So they reach the smoldering phases, which would have been lost in a static visualization. I'm just going to give you a few seconds to just track the movement there. In the left upper corner, you can see the leadwood and the Mopani, the green and the blue. Right, so that is all I wanted to show you. I see I'm still more or less in time to show you moveEZ, how it can be used, and then this important application that we are working on now. I just want to thank Professor Diane Cook from Monash University, really helped us to start this package that we developed. Also NGA Mass for providing funding for that visit. And then these slides I have put together in Quarto, and Tom Mock, we started with his templates, so I just want to give some credit to him as well. And thank you to all of you for listening.
Yeah, thank you very much for the very inspiring talk. Are there questions for our speaker or suggestions for other uses of the program? Zura, please.
Thank you very much. When the animation reaches the end and it goes back to the starting point, there is still a smooth transition from the last slide to the starting point. And I was wondering maybe if it wouldn't be more useful if that smooth transition wasn't there so that the eye can catch when we are rewinding back to the starting point.
Yeah, that's a good suggestion. Almost starting completely fresh, maybe have like a black screen or something to reset, as you said. But yeah, that's something we can look into. There's a lot going on. So that's why I think if you don't focus on something specific, you'll lose a lot by just trying to see everything at once. And yeah, I take that suggestion. Yeah,
Thank you.
Thanks.
Are there more questions? Suggestions? Do we have any questions from the online audience? Not so far. Ah, Zurab.
I also have a question. Would it make sense if there was a version where instead of drawing the entire area, you take its center as a single point and you show how that point moves around? I don't understand enough of data analysis
So
to
you
know if it
mean
makes sense or not.
the sample point and then suppressing maybe all the other regions from that grouping variable?
So when you had the shaded area,
yeah,
that we represent the entire area with just its center.
you can add that. In biplotEZ, we have alpha bags, not convex holes, and there is then varied center points that you can select, or you can change the size of the region. That's kind of linking to what you're saying. But we looked at a data set that has less observations, where it's basically one observation per time point. Then it's very easy to see movement. It's not as exciting when you look at it, but I think for interpretation, that is useful. Yeah. Thanks for the suggestion.
There's a question at the back there, please.
Thank you very much. I want to ask, like, how does the rotations fit in these movements? Can they fit in?
So the actual what is changing, are you throughout the algorithm? Is that what you're looking at or asking about?
I mean, those PCA rotations, like the Verimax, the orthogonal rotations, how can they fit in this movement?
So
Use them.
So if I understand you correctly, within the GOPA algorithm, we have an orthogonal rotation matrix. So basically what you're suggesting is doing a different kind of a rotation in that algorithm. Is that what you're asking?
Yeah.
So not in this version, right? You would have to go and look at the way that GOPA, in our sense, is working and incorporate a different rotation. But this is only one way of applying GPA. So I want to say, yes, it would be possible to try other rotation matrices, but this is only the orthogonal rotation matrix that is used here.
Can I ask you a question? The university produces probably tons of data that
Yes.
nobody studies.
Bring us the data.
No, one could investigate performance of modules, courses, lecturers, I don't know,
Definitely.
many variables, yeah? Students. Yeah?
Yeah. No, definitely. I never know where to get that data. Maybe someone can link us with the correct people, but that could definitely be interesting to
Definitely
track.
somewhere.
Yes.
Okay, Zurab, one more.
You have the data.
I don't, but I just want to add to the idea that Francesca proposed. I think it will be interesting to see if we can somehow detect the effect of AI on student performance, whether it boosts the marks or lowers them or pushes them in some corner. That could be one of the projects to look at.
Yeah, that could be one of the factors that we track. Yeah.
We have a question from the online audience. Please, you're welcome to ask your question. Can someone give the permission to speak, to talk? Just a second, please. Okay.
So shall I ask? Can you hear me?
Yes, we can hear you. Please go ahead.
Okay. Thanks very much for the presentation. I just wanted to ask if there is a way to incorporate categorical variables into the data set and then apply this method. I see we are currently using continuous variables. That is the P, we have the N, the data set with N and P continuous variables. Just wanted to ask if there is a way to incorporate categorical variables and then apply the method. Thank you.
Thank you for that question. So currently, the only categorical variables that we can factor into this is to either make it the time variable or make it like the grouping variable that you see with the regions on the screen now. So this version of moveEZ only incorporates PCA, which you're right, only for multivariate continuous data sets. But as we develop the package, it can later, we envision it to also incorporate multiple correspondence analysis, look at generalized biplots where you can have mixed variables. So it's definitely possible. In a different package which doesn't animate biplots yet, I have a GPA bin package which is specifically for multivariate categorical data, which constructs biplots and then also uses the same GPA methodology. But as I said, it's not animated yet. So you're welcome to go to my repository. The GPA bin algorithm is there, or the package rather, and you can play around with that. And then hopefully in version 3 or something of moveEZ, we'll have categorical biplot animation as well. Thanks.
Thank you.
Thank you so much. I just have a question on how to maybe, I'm thinking of maybe a publication. Do we have some publications or channels that may be having some animations, maybe in regards to the questions that we have on AI? Do we have some channels that accept some animations?
So luckily with online publications, I think there is an opportunity to embed HTML files or like GIFs that I have in here. Sorry, specifically the R journal, I'm just thinking now of my domain. They do have an online version and a PDF version. And in the online version, there's animations. And in the PDF, it's all static. So if the journal is not purely online with the HTML embedding, then of course it's not possible. But what you can do is through Figshare, and I'm sure there are other platforms, you can upload that HTML and include the link in your paper. I mean, it's not ideal having people move away from the paper, but that's one way of adding the animation there.
Excellent. No more questions from the online audience? No? Then if that is not the case, then let's thank the speaker very much again. Thank you.
Thank you.
And I have to give you a little thank you.
Thank you.
Our famous Bizarco magazine. And
Thanks.
Sophie sitting at the top can tell you everything about it later.
Wonderful. Thank you so
And
much.
thank you to the online participants. Yeah, thank you very much. And for those of you that are here, there should be some snack and drink outside as planned, but we don't know until we get there. Thank you very much. You want